full with metal, and so we have to fill it completely. And if we move our plunger too slow, we're going to create a little wave that's going to detach from the plunger. It's going to hit the other side of the hit the shot block in the die and reflect back. And I'm going to trap a pocket of air like you see in this upper right-hand picture. And that pocket of air is going to be forced into my casting. If I go too fast, then I'm going to cause this wave to roll over, and again I'm going to trap air and force it into my casting. And so again, when I look at my process design, I need to be thinking, or I need to work with my die caster to make sure that we're handling these types of concerns as well. It's not just enough to say I want to get a nice pattern for filling my mold, but I also have to make sure that I'm putting good metal in there and not metal that's caught up a lot of air and other oxides and things of that nature during my injection process. But the flip side of that is I also have to make sure I get the air out in front of the casting. I can do the best job in the world of actually making sure that I don't trap any air, but if I don't let air out of the cavity, I'm going to trap air no matter what. And so a general rule of thumb we look at is that we take the fill rate, or how fast I need to fill the casting, which is something on the order of 50 milliseconds for most castings, and I can take the volume of my casting, and I can come up with that flow rate, right? So if I'm doing a 100 cubic inch casting, I divide by the 50 milliseconds, that gives me a flow rate, and then I'll divide by 8,000 inches per second, which is roughly the 60% of the speed of sound in air in the die cavity. And what we use that for is to make sure that the back pressure of the air evacuating the cavity does not get too large. And so you see in this bottom right-hand corner, you see for different size vents, I get different levels of air pressure in the cavity. And the higher that air pressure, the more likely I am to have some porosity issues with air entrapment. And so as I get to a limiting case where I can't get sufficient area for venting, or I can't place vents in their optimum locations because of the casting geometry itself, perhaps I have slides or other features that don't allow that venting, I can start looking at things like vacuum die casting. And really when we do vacuum, we want to go to high vacuum, which is shown here with that high Q cast in the upper right-hand corner. And you see that as I drop that vacuum level even lower, really ideally below 100 millibars, I can dramatically reduce that porosity that I'm going to see in the casting. And so again, when we look at this idea of designing the process, in our design, if I can't tolerate porosity, I should start out up front saying this is going to have to be a high vacuum casting or something along those lines. Now we also have to control the thermal aspects of the process, and so typically die spray and the cooling lines in the die are going to be what we use to control the temperature of the casting. And just here's a great example here. If I look at a thermocouple in a die and I look at a number of cycles, what you'll see is I have this variation or a quasi-steady state that I reach. And really what I'm looking at is trying to design a process that will control both that variation as well as that average temperature like you see in the red. And so if I need that die to be warmer, then I design or colder, then I design a system that will actually pull that temperature down instead of allowing it to come up higher. And if I need that die to get even hotter, then I can shut some of that water off and shorten the cycle rate, and that'll help me heat that die up more. But again, we need to be able to start thinking about these problems early on, and when we talk about defects, it'll start really making sense why we have to watch out for these thermal type issues. Ultimately, the thermal control is what controls my surface and my internal defects, as well as my cycle rate or my productivity and my die life. So this is a fundamentally thermal-driven process, and so I absolutely need to understand that as best as possible. Finally, we have to worry about our dimensional control, and this is really, again, a thermally driven thing, but here we look at it not in terms of defects, but more in controlling the final dimensions of the casting. And so this is a nice little chart that shows you how things vary. My die steel was cut at room temperature, and so when it gets warm or it comes up to operating temperature, that die steel is actually going to grow a little bit. Now all my dimensions will either be a little large or a little small depending on whether it's an interior feature or an exterior feature. During the casting process, I'm constrained. I can't allow that casting to shrink any smaller, and so I build up a little stress, but I